Okay, let's begin our afternoon's session. The first speaker is Yang Shuo from Tsinghua University. She is going to talk about locally purified density operators for mixed states. Okay, let's begin.
Okay. Thank you. I would like to thank the organizer for inviting me here for such a big, very nice conference. And today I will talk about the locally purified density operators for mixed states, tomography, simulation, and topology. So this work is done with my students in Chengguo from Tsinghua University. And these are the, if you want to see some details, you can find it in this reference. I would also like to thank other collaborators, Dr. Jianhao Zhang and Professor Zhen Bi from Penn State University, and also my student Haoran Zhang from Tsinghua University. So this is the outline of my talk. First, I will introduce what is the locally purified density operator, and then I will show three applications of this LPDO, including the quantum state tomography, simulating noisy quantum circuits, and also symmetric-pathetic topological physics in mixed states. So actually, the LPDO is a tensor representation of a mixed state. Let's first see what is tensor. So we can use this Penrose graphical notation to express the tensor. If you have a constant, we can draw a circle without any outer legs. And if we have a vector, it has one index, then we have draw a picture like this with one open leg. And if we have a matrix, we have two indices, and we draw a picture with two open legs. And if we have a rank 3 tensor, there will be 3 outer legs. And if we have n indices, we can draw some picture like this with n outer legs. So this is a kind of graphical notation of the tensors. And for a quantum state, that if you have a n-spin quantum state, the coefficient function is like this. So this C has n indices, and then we can draw the picture like this with n legs. So this is a graphical notation for the wave function. And composition of this wave function that mathematically we can use the singular value decomposition. We cut it in the middle and we cut it as a matrix. And from singular value decomposition, we can decompose it just into 3 parts. U and V are unitary matrix, and this S is the singular value. So this S actually contains about the many-body entanglement. We can use measure the amount of entanglement. If you want to calculate the entanglement between this part and this part, we can first calculate the reduced density matrix of the left part. For example, we can first draw the whole density matrix. It's just the inter-product of it's the direct product of the graph and the kit. And then we have this kind of figure. We just put the wave function together. And to calculate the reduced density matrix of this A part, we can trace out the B part. By tracing out, I mean to do a summation of all the physical degree of freedom. Graphically, we can draw a line here. And this is the summation of all the degree of freedom in the B part. Since this part is a unitary matrix, then we finally get a line. So this is what we obtained for the reduced density matrix. So we can see that the diagonal elements are nothing but the square of the singular values. And from this, we can directly calculate the entanglement entropy from this kind of equation. So similarly, we can also trace out the A part and obtain the reduced density matrix of the P part. And we can also use this kind of equation to calculate the entanglement entropy. The result is the same. Cause the entanglement entropy of the entanglement between A part and the B part. We can see this distribution of these singular values is very important because it shows how large is the entanglement. Suppose all the singular values has then we can have the maximum possible entanglement entropy, which is log D, where D is the total number of singular values. This is the maximum possible entanglement entropy. And so this horizontal line actually encodes the entanglement structure. So using this kind of structure, we can visualize the entanglement within the system. Like we can, from the whole system, we can decompose into many small parts. And each part we can use a single tensor. And then the connection between these tensors becomes a network. And this is the idea of a tensor network. It's just a very direct visualization of the entanglement structure within the system. And we can also use this tensor network to represent the density matrix. The density matrix is like a matrix. So we can regard it as a row indices and a column indices. And for the pure state, that's the direct product of a bra and a pig. So here I draw a dashed line in between. This shows that it's a pure state. Or we can regard the bound dimension as only one. For the mixed state, we have some superposition of different components. Here, the line between them is at a larger bound dimension, depends on how many superpositions. So this is some graphical notation for the density matrix. So using the similar idea of the tensor decomposition, we can further decompose the density matrix into many small parts. Let's say here, if we cut it from this figure, we can get this figure is called the matrix product operator. For the pure state, it becomes something like this. So the one, we have a dashed line in the middle. This means the bound dimension, the inner bound dimension is only one. And also, if we have a mixed state, the inner bound dimension will not be one. It will be larger than one. It depends on the how much mixed states do we have. So this figure is what we call the locally purified density operator. We can see this structure more carefully and exactly at this kind of formula. And we have three kinds of indices. The blue one is the physical indices come from the density matrix. So the blue one is just the ordinary physical degree of freedom. And the green one is like the vertical legs. They actually describe the quantum entanglement. We call it the virtual indices. And also we have these red ones. The red ones are the inner indices. It's also called the Kraus indices. This is what only happens for this. We can use this to express the open system. For the pure states, this all the bound dimension of the inner indices will become one. So this part and this part are can decouple. So this is a pure state. But when decoupled larger than one, it becomes the mixed state. And this LPDO structure has been readily used to simulate thermal system and open systems. And the good thing of this structure is Hermitian and positive semi-definite by design. Because for every in the left column and the right column, so here is AG, and the corresponding one is AG star, the conjugate of AG. Then we see that this density matrix is Hermitian and positive semi-definite by design. And this is a very natural structure for the physical density matrix, because the physical density matrix also has to satisfy this condition. And if we group these two together, then we will get this MPO structure. But this MPO structure may not satisfy the positive semi-definite condition. And if you have a very low noise, so this decouple is typical of small constant, and it can be independent of system size. And because we have distributed all the mixed degree of freedom into n size. And we see from this picture, we have a locality to both the system and the environment, and it is a very efficient representation. because we can count the total number of parameters. So previously, the density matrix, the total number of parameters is exponentially grows with the system size. But now it only grows linearly with the system size. So that's the advantage of the tensor networks, because it have a very efficient description of the system with the locality. And I will show the first application is a scalable quantum state tomography with locally purified density operators and local measurements. The problem we want to solve is the quantum state tomography. So this idea is very important in characterizing and evaluating the quality of quantum states. It also serves as a crucial element in the arrangement of the quantum hardware and software. The basic idea is given an unknown state rho, how to experimentally determine what the state rho is. So this is we can do for some measurements, and this is the idea of the tomography. I guess people probably know the tomography in the classical world. Like if you unfortunately get injured and go to the hospital, probably the doctor will suggest you to do a test about this CT test. The CT is actually the abbreviation of a computerized tomography. That you take some pictures and do some projection measurements, and from this 2D figure you can reconstruct the 3D objects. This is what we do for the tomography in the classical world. And similar idea can be done in the quantum world also. For example, for the single qubit, we can choose a set of phases, and the density matrix can be expanded this basic like this. And we can measure some observable A and for many times, and finally get the estimate of this coefficient. So this coefficient is just the coefficient before this basis. And if we measure it many times, we can get enough information, and we can reconstruct the density matrix. So this is what we do for the quantum state tomography. For the unqubit system, we can do some similar thing and finally determine all the coefficients before the basis. And the difficulty is that the number of total measurements scales as 4 to the NQ. And it actually increases exponentially with the system size. So this is the difficulty in experiments. And there are some recent protocols to overcome the difficulty. And the one idea is to use efficient parameterization for the unknown quantum state. We can extract the density matrix either from matrix product state or from restricted Boltzmann machine. The idea is to reduce the total number of parameters, and then the difficulty will be reduced. And another idea is to use some scalable classical optimization algorithms that we can do some local measurements to get the expectation values. From this kind of local measurements, we reconstruct the whole state. And also we can do some sampling about the global measurements. So this means we do not measure all kinds of possibilities, but only some of them. And then we can reduce the cost. But the Paris scheme still have some limitations, like the scheme from matrix product state tomography only applies to the pure state, but for the quantum state in experiments are subject to noise. So usually we need to do this for the mixed state. And some global measurements cannot be integrated with quantum error mitigation techniques. Because of this quantum error mitigation, many proposed for local observers. And also, some classical algorithms are generally costly and cannot be generalized for higher dimensional systems. So that's why we propose our protocol. We have used a gradient method and local measurements to do this quantum state tomography. We call this scheme this gradient LPDO. Actually, we use the locally purified density operators to represent the mixed state, like this. And we also do some local measurements to reconstruct to get all the parameters in this LPDO. So the steps of LPDO is as follows. The first, we will obtain the local L local reduced density matrix for the size from the L neighborhooding size, and in this region, to measure all the kinds of combinations and get the coefficients, but with only the L neighborhooding size. And then we can define a total loss function. That this is the differences between the one from experiment and one being reconstructed. The aim is to try to minimize this loss function. We can use a variance of the gradient descent to minimize this loss function. Another simplification, so we only consider the adjacent terms involving the set J. So this we can get the gradient, and then we can update the local tensor A like this. And finally, we can evaluate the gradients at each step. And then we see that the complexity is only proportional to the number of different sites. And later we will show from numerical results that so this kind of iteration can convert in only log and iteration steps. Here are some numerical simulations. We first test one-dimensional critical icing model. This one-dimensional transverse field icing model is like this. We this parameter at the critical point, and we also get the ground state for bound dimension 16. This is serves as the tracking state for the reconstruction. And then we compare our results with the LPDO method and with another previous method using the maximum likelihood method. We can compare the different results. We plot the number of iterations 0.9 for different system size. We see that if we use this previous method, so the iteration step grows exponentially with the system size. However, using our method, we get this converted scale in only log n times. So actually, our method will convert much faster than previous one. And also, we can compare the maximum fidelity we can achieve. So this figure shows the maximum fidelity of the two methods. The right line is our method, is higher than the previous method. And this figure shows the convergence of stability. If you use the previous method, go up, goes down. Then it's not good because we don't know where to stop. However, if you use our new method, so the fidelity will go up and get converged. It will consistently converge to maximum fidelity. And so this fidelity is defined as follows. So for the pure state is like this, and for the mixed state, we can use this kind of calculation because it's there for the tensor network calculation. And the above results shows that our method surpasses the previous method in 3 steps: efficiency, accuracy, and stability. We can also check the one for the 1D Heisenberg model, and we take the Hamiltonian like this is the antiferromagnetic Heisenberg model, and the ground state will have the antiferromagnetic correlation. And we can calculate the digit correlation like this. And from the experiment, it should be something like this. And from our reconstruction, we can get the almost the same one. And the differences between two figures is shown like this. However, if you use the previous method, the differences become here. The previous method cannot accurately reproduce the correlation between the sets when the interval is larger than 3, because here the green dots here, so it's quite large. However, if you use our method, so it can capture most of the long-range correlation. And we can also one with noise. So previous result of pure state. We can add some local noise to the density matrix, and for example, we can get some depolarizing or bit splitting or amplitude damping and phase damping, this kind of different noise channels. And we can see it. So when we add some noise, you can generally reduce the reconstruction fidelity, and cannot be improved by only increase this peak kappa. And this is because the local measurements cannot distinguish the mixture from entanglement and noise. Also, the depolarizing one or this bit splitting noise, it has a larger challenges because these models are studied in nature and directly induce the mixture across different trajectories. And we can also compare the one with different kind of measurements. Perhaps previously we only took L equals to 2. Then we can enlarge this L. We see that increasing this L has significantly improved the accuracy for all types of noise. For example, for L equals to 4, the reconstruction fidelity for existed for 0.985, even for the 25th is like here. And so although we also observe the pure dependence of the reconstruction fidelity and the pure, so the lower panel, the pure reconstruction fidelity, they have the same things. And this means that if we want to have a larger fidelity, we need to increase L. However, the cost will also increase exponentially L. So there must be a trade-off between the accuracy and the efficiency. And fortunately, so the moderate size critical system with typical noise levels, so very small L is sufficient to have a high fidelity reconstruction. And we can also generalize this idea to 2D systems that we can choose a random test with the boundary free for reconstruction. And we also perform some local measurements. There is on a 1x2 cell and also 2x1 subsystem. And we can update also local measurements covering this size. And here we show the fidelity as a function of the system constructed bound dimension. And we see the average fidelity is 0.95 for 8x8 steps with a bound dimension 4 here. And see that, so that this 2D tensor network is constructed layer by layer. And for each time we also truncate it to kite to this square after each contraction. And so the fidelity is still quite high. And this is also the first study of tensor network state tomography for two-dimensional systems. And we can also do like we use this kind of superconducting processor with 7 qubits, and we apply this random to the product state. So we can measure the observable using many strokes. Here, when we do the simulation, we only mitigate the measurement errors, but not the throughput errors. Every throughput has some errors. And the common state tomography is to learn about the noise information. So we see that they plot the loss function as a function of iterations. For different bound dimension D, they all get converted very fast. And even with a very small inner bound dimension. And you can also choose a larger bound dimension. You can see the loss of function will be smaller for the larger inner bound dimension. And this means so the result will convert very fast. And how about the local observables? We can compare the one from measurements, one for each kind of figures, so the left one is from measurements and the right one is from reconstruction. You can see they are almost the same, right? They have high consistency. And here we only choose the inner bound dimension equal to 2. And for this very small inner bound dimension, and also D is also very small. It's actually already serves as a good approximation for noisy quantum circuits. And this result also validating the performance of our tomography scheme. And the summary of the first LPDO on this locally purified density operator for mixed states, and we use only local measurements. And so this method can enhance compared to previous methods using relying on the metric fallacy. And we have also extended the sensor network quantum state marketing. And also some other quantum error mitigation schemes for higher dimensional systems. And now let's see the second application of this LPDO. We can use this kind of structure to simulate the noisy quantum circuit. Each layer has a tensor product of the 2-qubit per random gate for the blue one. So the blue one is each drawn randomly and independently from the uniform distribution on the unit of the group. So U is unitary. And we can also add some noise channels after each gate. So, for example, we can add a 2-qubit polarizing noise channels like this, and then this epsilon is the 2-qubit error rate. Experimentally, usually it has the order of 10 to the minus 2. And so we can see this noise channel more carefully like this. The tensor representation of the noise channel has the operator sum form like this. And if you draw the tensor diagram, it's like we apply this E on both sides of the density matrix. And we also need to do a summation about this regroup this E and row like this. And we can change this row from a matrix to a vector. So that becomes a vector row. And then these two E's, we group them together, a super vector form of this U. So this is what we draw here. It's this actually a common channel. And we see that the inner bound dimension of this LPDO is also called a Kraus index. That's because this noisy quantum channel can increase the bound dimension of the inner indices. For example, if you have this noise channel acting on this row, we see that this becomes here. So the total bound dimension in the inner indices will be increased by this noise channel. For example, for the single bit fleeting noise, it will increase the bound dimension times be covered by 2. And for the depolarizing noise, it will times be covered by 4. General LPDO, you can have some intuition about the effect of each bound. So the unitary 2-qubit gauge in the virtual bound dimension, the green one, and the noise channel will increase the inner bound. The right different effects. So roughly speaking, so this virtual bound dimension represents the quantum entanglement. And this inner bound dimension represents noise. This is our intuition. In principle, this big kappa equals to dp is enough. So dp is the total physical bound dimension. But actually, it may require another the virtual bound dimension. if you put a larger data, the bound dimension of worker units, we can also reduce the overall complexity while maintaining accuracy. So this bound dimension and this bound dimension so can be converted to each other, because what we concentrate is the total density matrix, the inner structure. So finally will be traced out. So actually they will have the same effect. Consider them as a whole. So if you consider as a whole, we can regard the density matrix from this kind of picture to this kind of picture. So this is like a projected entangled pair state of the size 2 by n. So here is the length is 2, and here the length is n. And the physical indices now we draw is out of a plane. Just within the plane. So this is unified to look at this LPDO. And if we look at it like this, we can draw a dashed line here. We can consider the entanglement between this part and this part. So if the entanglement satisfied every law, we can see that this is so suitable to use this kind of structure. So if a quantum state will satisfy the entanglement error law, the original mixed state can be represented by this LPDO. So in this kind of framework, both the inner bound and the vertical bound LPDO become the vertical bound of text. And we can actually see what are the effects of the different checklist for a noisy quantum circuit. First of all, for the single qubit unitary gate, it only acts on a single side. So this gate will not alter the we can see that the increase of the entanglement is become 0. For the 2 qubit gate, you select this one. So this one will increase the bound dimension of this worker bound. And then we can see how many times it cuts the dashed line. From this picture, we see that if we apply a layer of this 2 qubit gate, it will cut the dashed line by 2 times that. So this means a layer of 2 qubit gates can increase the entanglement by at most 2 CU. So CU is the entanglement growth for the single 2 qubit gate. For example, for the CNOT gate, CU equals to 2. And we can also check the one is single qubit noise acting at this. And this one will increase the inner bound dimension. And we can see for the L side, so this distance is L, it will cut the dashed line for L times. For the layer of the single qubit noise channels, so it can induce the change of entanglement proportional to L. And we can also noise is like this. So this one will cut the dashed line for L plus 1 times. In this amount proportional to L plus 1. And we can sum all of the effect, all of these effects. You can see for the typical brick wall quantum circuit of depth D, the total entanglement growth will like this. And for the larger D system, we can see that this is proportional to D, epsilon, and L. So this is epsilon is the 2 qubit error rate, and L is the distance from here to here, and the D is the circuit depth. We can see that a supervector from mixed state generated from noisy circuit is a depth getting lower than this inverse of error rate. So if this L will only proportional to L. So this means that so the surface depth, if it is not too deep, the entanglement will not be very large. So this depth scaling ensures an efficient capture representation for this PEP's view vector. So this is also ensures an efficient LPDO representation. So in other words, the circuit is very, very deep, and we can extend a filter of this LPDO simulation. And then this the circuit is deeper than the scaling behavior of this. So this is our conclusion from this analytical analysis. This means that if the circuit is not very deep, we can still use this LPDO. But if the circuit is too deep, the LPDO may not be a good representation. And we can use this kind of scheme to do the simulation of the noisy quantum circuit. And we also need some truncation methods. This is how we truncate, but you don't need to worry about the details. So I just want to emphasize that we actually add the bound dimension. We can use this kind of scheme such that we can truncate the inner bound dimension and also virtual bound dimension simultaneously. And for this brick wall quantum circuit, people have done some calculations. The matrix part operator. They see that so for this entanglement entropy, if it's cut in the middle, so they actually plot the maximal until entanglement entropy and as a function of the circuit depth. So at first, and then it will go down. So this P is actually their error rate. It's a 2-qubit error rate. So this is why they have this increasing and decreasing behavior. This is because when we add this kind of gate, it will increase the total number of entanglements. However, we still have noise in the quantum circuit. So the noise will destroy the entanglement. So finally, when the circuit depth is very, very large, so all the entanglement will be destroyed. And so this means that we must have this increasing and decreasing kind of thing. And also they also check the circular depth, that they can check the circular depth and this maximal entanglement entropy are proportional. And here in this figure, they plot the maximal entanglement entropy as a function of proportional. So if the error rate is very large, so people cannot go to very deep circuits. So this is also intuition. Like for the quantum simulation, the total number of qubits is actually not that important. But the most important thing is the error rate. Because even if you have a large number of qubits, if the error rate is large, you cannot do many quantum operations. So the entanglement will go down. And only the one in this part can have some quantum advantage. The result shows that the previous result shows that the maximal until entanglement entropy first increase and then decrease, and the maximal entanglement is still at this, and then also independent of N. And we can do the similar thing. For example, we can use our LPDO structure to do the similar simulation. And here we compare the entanglement entropy for different methods. So the dashed line is from exact localization, because we can use a very small size system, and we can do it exactly. Trends. And if you use the ordinary matrix part of the operator method, So the LPDO, we found a different structure. So the entanglement entropy will first increase. So this part is similar to the MPO. However, when the surpass this critical point, it will not go down, but this will be horizontal. So that's the difference. So basically, we have two regions. One is called quantum region. So this is entanglement entropy will always accumulate, and so this part will potentially offer quantum advantages for systems with much larger sizes. And also there's another region. So this region is what we call for the classical region. So this part will dominate by noise effect, the highly depolarized and mixed systems. And we can see for the MPO, they can cognitively capture all the trends in both parts. However, for the LPDO, can only accurately describe the entanglement dynamics, but not the classical region. And this dashed line marks the transition point. So LPDO can exceed MPO in terms of both accuracy and efficiency in the quantum part, but it shows some limitations in the classical part. To see this limitation, we can about the fidelity between this MPO and LPDO. Is the exact one. The super vector fidelity, and we can see from this picture from LPDO, and so the cross, the gray cross, is from the exact localization or from the MPO without any truncation. So we see that the fidelity is comparable for this line and this line. And if we choose a truncation of this MPO, and so this LPDO is actually performs better than MPO with truncation. So, but if we have a larger error rate, so this region will become smaller. By the appropriate answers when simulating noise circuits at different error rates. This kind of MPO. However, if the error rate is small, we can use LPDO at least in the quantum region, because LPDO is actually much more efficient. When we do the truncation, we can use a smaller bond dimension. And this right dashed line actually indicates the transition point. So from the fidelity, we have this transition point. And the transition point is actually characterized the critical, the we call the optimal depth. And also, previously from this entanglement entropy, they also have a transition point. And we can put them together in this figure. We can plot as a function of different error rates. Now we see that they almost collapse, and we can fit the lines. It's just almost anti-proportional to the error rate. So this result reveals that the failure of LPDO simulation beyond the optimal depth and the prediction. So this optimal depth should be anti-proportional to the error rate. Namely, when the depth is smaller than this, so LPDO can be used. And when the depth is larger, so LPDO cannot be used. And also see that for different kinds of models and different configurations, and we can check this for different random gates and for different spin models, randomly preserving each gate with a probability p. This results in error rate, effective error rate of p. So we see that all these kind of things the O class. So this marks the universality of our theoretical formalism. It can be used to how large we can go for how deep for the quantum surface. So this means that the optimal depth is determined solely by the effect of noise strength and regardless of the unit or the gates involved. And so simulation can effectively capture the overall trends in both regimes. It may violate the positivity condition for a density matrix. To check whether the density matrix is semi-positive definite, we can calculate the threshold, which is it shows the sum of the single values. In the density operator, then this threshold will be larger than 1. For depth, and then we see the threshold it will be larger than 1, right? So this peak of this maximal threshold will be lower than the optimal depth we introduced before. So we see that after completion, this MPO fails to preserve the positivity condition. However, for the LPDO simulation, because by design it's the positive semi-definite local positivity. So this means that if you use this which is accurate, it must violate the positive condition. So this shows the fundamental limitation of LPDO. We can first get the MPO and then project it to approximate the LPDO. So we can optimize this loss function comes from the MPO simulation and from LPDO, which is similar to MPO. We can use some optimization schemes based on the gradient descent local tensor like this. And here we show the results. So the lower panel shows the projection fidelity for the MPO projected to LPDO. You see here at the critical point, by MPO and LPDO deviate. So this shows the fundamental limitation of the LPDO implementation. So the LPDO trajectory cannot be directly corrected back once it is destroyed here. And we can also check the effective capacity of LPDO. So we can directly implement the projection from the exact density matrix of a very small system like N through 8. Here we show the projection fidelity at the critical point. We see that here, this is for chi to 24, and the inner bound is 4. Actually, it's similar to here, right? So this the one here is for chi to 14, but this larger inner bound. So the difference between this and this is that the different bound dimension of the inner bound and the vertical bound. So this means that equals 50. So this kind of scheme is quite reasonable. And the summary of the second part is that we have clarified capacity and the limitations of this LPDO simulation of noise quantum circuits. Okay, we also observe a critical point between the observe the universality of the critical scaling. The optimal depth is anti-proportional error rate. It also offers a statistical approach to estimate optimal depth of any quantum surface. The dynamics in the quantum region. So although it does not work very well in the classical region, because the classical regime does not have much quantum advantage, and various MPO simulation methods. So this is the second part. Let me briefly mention the state to the open quantum system. For this kind of system, we can have density methods with these. Actually, two types of global symmetry. One is called the strong symmetry or the exact symmetry. To apply this group of operations on one side of the row coefficient against the phase here. And another symmetry is called the big or the average symmetry. T. This means we need to acting on both sides of density metric. Then it will come back to the original density metric. So there are different kinds of symmetry. Already have this strong symmetry, then the weak symmetry must be satisfied. However, there are some other possibilities that the strong symmetry do not satisfy, but the density matrix satisfy the weak symmetry. In fact, if you apply some symmetry action, it can project one element vector to another element vector. But when we consider them together as a symbol, we still have the symmetry. And we can use this kind of locally purified density operators to show the symmetry. This is a part of the tensor network. And the red index is the physical index, and the blue one is the inner indices to show the mixture of the different components. And the black bound at the just show the working indices. For the strong symmetry, this means that we on this physical left, so some action will take on the working indices. Not only we have some additional structure on the working indices, but also we have some additional transformation on the inner indices. So you can compare this figure and this figure, you can see something more here. So that's the different action of different kinds of symmetry. So because we have this kind of structure as a framework to systematically classify and construct the ASPD. Without the internet, people have already done the classification and construction for the ordinary symmetry quadratic topological space for pure space. But now we can generalize this idea for the mixed space. We can even construct a simple example of the intrinsic ASPD physics without the pure state counterpart. Let's directly see the example. So we can consider the strong symmetry like this and the weak symmetry like this. And for the of the group structure. And the primary example satisfied this kind of symmetry is the cluster state. The antenna is like this, and the ground state should be like this, called the decorated domain wall structure. Which means that when these two sigma are proportional, parallel to each other, and the tau should be to point right. then this power will point to the left. Now we can write down the tensor structure. These are the non-zero tensor elements for this kind of order phase. If we apply the transformation on the physical lab, so this X will come down on the virtual X. This is for the one symmetry, and this is for another symmetry. The idea to go to the ASPD phase is to extend this tensor structure to we have some other additional legs for the inner indices. And we can construct the classical mixture of the different components. Then we can the kind of density matrix satisfy this strong symmetry and this weak symmetry. Use the trivial extension of the group structure. And this kind of tensor, and we can check the symmetry action. For the strong symmetry, so nothing comes out in the inner bound. But for the weak symmetry, we have some additional X on the inner bounds. This is what we call the particular order phase. And we can also do that for a non-trivial group extension. We can change the big symmetry like this, and so the symmetry action on the tensor will have additional M here. So this M cannot be decomposed into two parts on two different legs. So we can check this U. This U does not have the original characterizes do not have this U symmetry. But if we apply this U on both sides of this density matrix, this rho has satisfied this weak symmetry. So the tensor we have constructed here, it does not correspond any characteristic symmetry for that topological phase. And so this tensor has the same fixed point as the decoherent order phase, but with a different structures. Okay, let me have a summary. So we can see from the previous results that locally purified density operator can present the locality between system and environment. And we can use it for many-body computation, quantum information processing, and also quantum physics and quantum matter. Generalize the idea to two dimensions, and we can also propose some powerful algorithms for this structure, and also we can also use this to systematically study the mixed state topological order. I hope I have convinced you that this is LPDO is really an interesting, broad, and unexplored world. And with that, I would like to thank you very much for your attention.
Thank Yang Shuo for her interesting talk. Any questions from the audience?
Space. So basically, my question is, what's this inner bound means?
Inner bound is like when you write a density matrix, it's actually the superposition of many different components, right? The inner bound actually represent the mixture of the different components. Like if you have a pure state, if the density matrix made by the superposition of two components, the classical mixture of two components, then the bound relation will be 2. So it depends on how many classical mixtures the ensemble of the different components, and also related to the quantum knots.
Maybe another question. So why this weak symmetry acts on this inner bound?
Yes. So let's see here. Symmetry. If we apply this U on the physical leg, so inner bound will have some additional actions, right? And this M and the other side, M star, will cancel. And then there will be nothing here. So this one and the other one will cancel this. And then it will become come back to the density matrix.
So according to the definition, your Heisenberg model actually satisfies the weak symmetry of SU2 group. So I'm wondering, in your LPDO simulation, did you try to preserve that symmetry? I mean, in the first part, you mentioned your simulation for the Heisenberg model in 1D and 2D, right? And actually, the Heisenberg model satisfies the weak symmetry of governed by the SU2 group action.
So this the third part we consider. And for the numerical simulation, yeah, maybe in the future we can also consider the symmetry action. So to simplify the tensor operations.
Thank you.
Maybe a trivial question: is this LPDO scheme adaptable in higher dimensions when there is no presence of a lattice, say in the glass or something like that?
Yeah. So for the pebble structure together with the pebble. Yeah. And also in the third part, we actually have constructed some simple structure of tensors with this intrinsic ASPD figures in 2 dimensions. We have more details in the reference.
Is this LPDO capable of detect the topological structure of the 2D surfaces? Say, if we consider a LPDO on a sphere or on a torus, and we design the LPDO network according to its topological structure, is the result able to detect this?
Yeah, I think so. Like for the one-dimensional system, this kind of symmetry, if you consider like 1D10, there will be some edge state at the end of this 1D system, right? For two-dimensional system, it's also we will have the edge state on the of the 2D surface. Yeah, I think people can detect this like the normal one, like topological insulator, something like that.
Thanks.
Further questions? Okay, if there's no further questions, let's thank the speaker again. Okay.